Okay, so this is the second day over section 2.8, the last section out of chapter 2. The last section out of chapter 2. Just so you guys know, again, I believe the quiz says on Tuesday of next week for the derivatives quiz. I might push that. I feel like we need just a little bit more time. I want to finish the notes today. Maybe I'll give a work day. Maybe I'll give a work day on Monday, then we'll review Tuesday, and then we'll put on Wednesday. I think that's much better. And that way, that would give you, if we do that, then we'll quiz on Wednesday, probably review Thursday and Friday. That would push our test to Monday. So that's okay, right? But it will be a 2-day test, so it'll be Monday and Tuesday. Can't keep pushing it. We'll get to everything to do that. All right, so what were we learning in this section? We are learning how to find the derivative as a function, right? How to find the derivative as a function. What does that mean? That means that we're going to create an equation that when I input the x value, it's going to spit out the slope at that x value, okay? And it's going to be generic. So we're not gonna plug in anything for x. We're gonna leave x, but then send h to 0. Okay, send h to 0. Somebody in my 7th period asked earlier on. I gotta do this, or this is gonna annoy me. I don't know why this doesn't save. It's annoying. Okay, there we go. Somebody in my 7th period asked, so what's the difference between when we do like the f of x minus f of a over x minus a, limit as x going to a, and this whole difference quotient thing? Why don't we ever use the other version? I don't know. It's just what I like to use. In my opinion, I think the difference quotient is more applicable in a lot of ways, and it's just easier to get rid of just an h in the denominator rather than trying to get rid of an x minus a, right? Because we have 2 ways to write a limit. The limit as x going to a of f of x minus f of a, write a derivative, not a limit. Limit as x goes to a of f of x minus f of a over x minus a. That's one option, or the limit as h goes to 0 of f of x plus h minus f of x, and h, right? These 2 things should always compute to be the same thing at any given point. Always. If you don't, you screw something up. These should always be the same thing. Okay? So it's just easier to eliminate an h out of the denominator rather than an x minus a out of the denominator. That's why I like to use this difference quotient thing. So let's do that. We've got the square root of x. Let's find the derivative of f prime. And we're going to state the domain of f prime as well. Okay, so let's use that difference quotient. Let's say we've got the limit as h going to 0 of f of x plus h minus f of x all over h. All right, let's plug it in. Let's plug in x plus h. So this is going to be the square root of x plus h. Okay, that's nice. That's easy to plug in. There's no reducing there. Minus f of x. Oops, I don't need to write f of x. We know what that is. All divided by h. Now, is there some way to get x out of the denominator, h out of the denominator by itself? Or to try to reduce this down so that h is not alone in the denominator? We know a method. What do I want to do? Multiply by the conjugate, right? Multiply by x plus h plus radical x over radical x plus h plus radical x. Again, that I always want to multiply by the conjugate because when I FOIL the numerator, the inners and outers will cancel. So first here, radical x plus h times radical x plus h just gives me x plus h. Inners is these 2, and it's a negative. Outers is these 2, and it's a positive, which will cancel. That's the reason why we do the conjugate. Radical x times radical x is just x, and it's a minus, which is really convenient there. You see that? Do not distribute in that h, though. H times radical x plus h plus radical x. Don't distribute that in because it's going to cancel. And it's going to cancel right here, leaving me a 1 over radical x plus h plus radical x. That's as reduced as I'm going to get. So now, oops, got my eye. Let's find the limit as h goes to 0 of that thing. Okay? If I send the limit of h going to 0, well, that's going to turn that to 0, which means this is going to be 1 over, okay, blue, please. 1 over radical x plus 0 is radical x plus radical x. Well, radical x plus radical x is, I forgot my 2 radical x. Gone are the days where we will have to rationalize the denominator. That is completely fine to leave it like that, okay? 1 over 2 radical x. That is f prime. F prime of x is equivalent to 1 over 2 radical x. Now, let's state the domain. Now, please understand what we just did. We just found an equation at any x value. We can plug in the x value, and it's going to give me the slope of that tangent line. All right, so you want to find it at 4? Great. 1 over 2 times the radical of 4, which is 1 over 2 times 2, which is 1/4. The slope at x equals 4 is 1/4. All right, now let's state the domain. First off, the domain of any radical is x is greater than or equal to 0, right? As long as there's nothing else with it. However, can I equal 0 in this case? No. So all I have to do is just go no. So there's the domain. Questions about that? Good there. Let's take a look at this one now. This one's a fun one. Got to get out my notes for that. So find f prime, find the derivative. So we say the limit as h going to 0 of f of x plus h minus f of x all over h. The more complicated the function, the more complicated evaluating the derivative. Like, I've got x in both numerator and denominator, and there's operations happening to it. All right, so this is 1 minus x plus h over 2 plus x plus h minus, okay, so that's just f of x plus h, minus f of x all over h. Let's just look at the numerator for right now. Let's not forget about this over h, but let's just work with the numerator. Let's distribute in the negative here. 1 minus x minus h over 2 plus x plus h. Okay, I guess that's all we did. Okay. Should have just done that above it and carried on. But nonetheless, I need a common denominator here. Now, be careful. You might think that, oh, just the right side needs an h. No, these are different factors, aren't they? Those are 2 different factors. Okay, so here's what I have to do. I'm actually going to move this over just a little bit. That just happened, right? My screen went black, right? I was going to say, like, did I just go crazy for a second there? All right, so this one needs a 2 plus x. And this one needs a, yikes, 2 plus x plus h. Okay, let's multiply in on the top. This is going to give me a 2 minus 2x minus 2h plus x minus x squared minus xh, all divided by 2 plus x, 2 plus x plus h. Okay, minus, okay, if I distribute a 1 in, that's the same thing, right? 2 plus x plus h. And now let's distribute a negative x. Negative 2x, negative x squared, negative xh. Sorry, kind of cut off on there. That's an xh there. 2 plus x, 2 plus x plus h. Okay, I'm going to subtract these two numerators, right? Okay, so I'm going to take a 2 minus 2. I'm going to take a negative 2x and a negative 2x. I'm going to take a positive x and a negative x. I'm going to take a negative x squared and a negative x squared. And again, I'm using the same signs here because of this minus sign in between that, right? We're all understanding that. And this negative xh and this negative xh. And that's going to leave me with negative 2h minus h, right? Negative 2h minus 1h. So negative 3h all over 2 plus x, 2 plus x plus h. See, the difference quotient will cancel a lot of things out. Now, this is all still divided by h, right? So I'm going to multiply by 1 over h, which is so convenient because that will cancel now. Which is going to leave us with negative 3 over 2 plus x, 2 plus x plus h. Okay, let's find the limit as h goes to 0. Well, the only thing that I need to plug 0 into is right down there at the denominator. So this is going to actually be equivalent to negative 3 over, well, look, that's 2 plus x over 2 plus x, or sorry, 2 plus x times 2 plus x. And there's our derivative. Negative 3 over 2 plus x squared. That's f prime. So again, what is that saying? That's saying at any given point along that rational function, if you take x equals 3, I don't know, negative 3 over 5 squared, right? Negative 3 over 5 squared. So negative 3/25 is my slope at 3, at x equals 3. So this is a function that will spit out a slope to you at any given time. Questions about that? All right. Now, there are other types of notations that we have. I am going to be sticking to the f prime notation. You could also use y prime, but I just want to talk about a couple other notations in case you take calculus at a different level. And we will actually use a different notation. We'll use this other notation, which is called Leibniz notation, once we get to differentials and related rates. So it's good to know if you ever see it, if you're ever like looking up like, okay, how do I do this? And it looks a different way. It might just be a different notation on the derivative. So f prime of x, another way to write f prime of x is y prime, right? F prime of x is equivalent to y prime. It's also equivalent to dy dx. That's how we say this, dy dx. AP Calc uses dy dx. That's like that. They use that more than f prime. I don't know why. That's just the way the AP test does it. And that is Leibniz notation. That's the other big one that a lot of people use. That dy dx. That's the Leibniz notation. And Leibniz is just a really famous mathematician. He basically wrote the book on calculus after Newton. Another way to write that is df dx. df over dx. This d over dx is kind of like saying the derivative of. So if you say dy dx, that's kind of saying the derivative on y, the derivative with respect to y. D over dx of f of x, that's another way to write it. I hardly ever see this. I don't know. I never see that. I see Leibniz notation a lot. I see dy dx. I see d over dx of f of x. But I will be sticking to f prime of x or y prime. That's the one I like to use. Okay. The D stands for differential. The D stands for differential. Okay, derivative and differential are kind of similar words. Differentiation operators, blah 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 blah. Yeah, this is another. Sometimes they write it like this way. Like this. Like this is dy dx at x equals a. This is saying the derivative of function at a, or using this brackety type thing. That means evaluate it at that moment, like at 3 or whatever. Okay, one other thing that we're going to talk about is when a function is called differentiable. Differentiable. A function f is differentiable at a if f prime of a exists. If f prime of a exists. That's basically the best way to put it. It's differentiable if f prime of a exists. If it doesn't exist, it is not differentiable at that moment. Like, for example, in the last problem, we finished with a 2 plus x squared. What would have happened if you plugged in -2? The denominator would be 0. It's not differentiable at 0 then. Okay. Going back to our square root function that we did. What would happen if I plugged in -2? Oh, come on, non-real. It's not differentiable at that moment. The slope is not able to be evaluated, basically. Okay, we got to find it. To talk about something as differentiable, and this will actually connect into continuity as well. Okay, we're going to talk about when things are continuous and differentiable. Okay, so let's investigate the square root function. Or not square root function, excuse me, absolute value function. Where is the absolute value function differentiable? Well, we've really got two options for the absolute value, right? If the number's positive or if the number's negative. Okay, let's consider both cases then. If x is greater than 0, if x is greater than 0, what does the absolute value of x equal? If x is positive, what does the absolute value of x equal? X. Right? Okay, I'm going to consider this case. All right, let's find it. The limit as h goes to 0 of f of x plus h. Absolute value of x plus h minus the absolute value of x all over h. Okay, if the absolute value of x is going to be equal to x, h is always going to be positive. So I can take off the absolute value sign now of x plus h and also take off the absolute value sign of x. Okay, look what happens. This reduces to 1. The limit as h goes to 0 of 1 is, the limit of a constant is the constant, which makes sense. Think about the graph of the absolute value. Think about the V shape. What's the slope on the right side? 1. Does it ever change? No, it's always 1. The derivative on the absolute value of x is always 1 on the right side. Okay, let's consider if x is less than 0. Well, if x is less than 0, what is the absolute of x actually going to equal? The opposite, negative x, right? Okay, so let's evaluate that. The limit as h goes to 0 of Okay, so now this is going to be, I've got to put a negative in front of it. Negative x plus h minus negative x, right? I'm just emphasizing that with parentheses there. Because we're assuming that x is negative, so we got to flip it to be the opposite. Watch what happens. Negative x minus. Somebody's just really not want us to do calculus today. I think it's my cord. It's Catalina. She broke it. Negative x minus h plus x all over h. And look what happens now. Presto changeo. What is this reduced down into now? Negative 1, which makes sense because what is the slope on the left side of my V shape? Negative 1. Now, see, the limit exists. See, f prime of a exists for every value on the right side and for every value on the left side. So we can state that the absolute value function is differentiable for every value greater than 0 or less than 0. What value have we not talked about yet, though? At 0. Third case. If x equals 0, now watch what's going to happen here. The limit as h goes to 0 of the absolute value of x plus h minus the absolute value of x all over h. Well, if x is 0, that's true, right? Which is, okay. We've done this before. We've found this limit before. You may not remember, but we've done this. We found this limit. Let's run it through just in case we don't remember. Okay. Now, to evaluate the limit like this, we need to evaluate it from the left side and the right side. Okay. Left side limit. The limit as h goes to 0 from the left of the absolute value of h over h. Well, if it's on the left side, this is negative, right? So the absolute value of negative h, or sorry, the absolute value of h would actually equal negative h, right? Which is negative 1. The limit as h goes to 0 from the right, okay, of absolute value of h over h would just, well, if it says on the right, this is positive, absolute value of h is just h. What did I show here? The limit does not exist. The limit as h going to 0 of the absolute value of h over h does not exist, which basically said this limit does not exist, which says that the limit as h goes to 0 of absolute value of x plus h minus x over h when x is 0 does not exist. You know what that means? It is not differentiable at 0. It is not differentiable at 0. The absolute value function is not differentiable at 0. Let me show you what I mean. Okay, so that's a little bit steeper than it should be, but that's the basic form of an absolute value, right? Okay, if I wanted to draw the tangent line here, you know, I should actually make it come to a nice clean point because it would be here, 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 and then would it ever round out at the bottom like a quadratic would do? Like a quadratic rounds at the bottom. So if I kept drawing the slopes, it would be here, here, less, more, right? But for an absolute value, it's going to go -1, -1, -1, -1, -1, -1, positive, 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 right? It's not rounding out at the bottom. It's coming to a nice, clean corner point. So if I tried to draw the slope of the tangent line on that corner point, I'm not going to be able to. I am not going to be able to. So if f is differentiable at a, then f is what's called continuous at a. That's our next theorem here. If f is differentiable at a, then f is continuous at a. Now, why am I showing this now, right after that last problem? You're probably like, whoa, that's something different. It's not actually. I just showed that the absolute value function was differentiable everywhere but 0. You could find the derivative of the absolute value function everywhere but 0. Is the absolute value function continuous? Yeah. Are there any gaps or breaks? No. It just makes a V. Never have to lift up my pen. So I know, even though I had a continuous function, it wasn't necessarily differentiable everywhere. That's not what I'm saying here with this theorem. I am saying if f is differentiable, then it's continuous. If f is differentiable, then it is continuous. If I can evaluate the derivative, you know the function is differentiable. Or sorry, if you can evaluate the derivative, you know the function is continuous. Okay? If the limit exists to evaluate the derivative, then you know the function is continuous. But the converse of that statement is not true. Just because the function is continuous does not mean it is differentiable everywhere. Just because it is continuous doesn't mean it's differentiable everywhere. Okay, so how can a function not be differentiable? Right? What are the scenarios? What are the situations where I'm not going to be differentiable anymore? Well, there's a couple. Okay. The first option is when you have a vertical tangent line, or we would call that a vertical asymptote. If you've got a vertical asymptote, then the function is not differentiable on that point. Hey, that's continuity right there, right? That is continuity right there. If I have a vertical asymptote, it is not continuous at that vertical asymptote, which means it's not differentiable at that asymptote. Another place, here, that's a jump discontinuity, right? An infinite discontinuity is not differentiable. A jump discontinuity is not differentiable. A removable discontinuity is not differentiable. But there's actually a couple more that we get to add to this list. If the function ever comes to a nice, clean point, like the absolute value function, it is not differentiable there. Okay? I will call this a corner point. The book calls it a kink, which I just think that word is weird. I don't know. I'm going to call it a corner point, but if you ever see the book call it something different, just know that's what it's calling. I believe that's what it calls it. Yeah, don't say that. Don't. That's just rude. I heard that, and I don't know how to hear that again. I swear that's what they call it. Well, I probably gets to it later. But a corner point. Oh, see, it calls it a corner right there. But later on, it might call it something different. So a discontinuity or a vertical tangent. Now, we might think vertical tangent as only a vertical asymptote, but it actually includes something different too. If the function ever bends through any given point and goes vertical at any given point, if I try to draw the vertical, or try to draw the tangent line at that point, what's the slope of that line? Undefined. So if the function ever goes vertical, if the function ever, even if it bends through, it is not differentiable at that point either, because the slope would not exist. The slope is undefined. Okay. Yeah, this is just kind of like zooming in on any corner point. If it's a corner point, I can't draw a tangent line right on that point. That's why it's not differentiable at that point. We can also take higher derivatives. Okay, we can also take higher derivatives. You know how we took a single derivative? You can take a double derivative. You can take a triple derivative. You can take that process going forever and ever if you really wanted to. And we will learn the implications of these derivatives as well. This is called the second derivative. A double derivative is the second derivative. It's just basically finding the derivative on the derivative. Okay, and we will again learn the implications of this. But how do we evaluate it? This is just the Leibniz notation of it. Instead of saying dy dx, they say d squared y over dx squared. This is again why I like this prime notation, because you just read another apostrophe there. We did this problem yesterday. X to the third minus x. The derivative of x to the third minus x was 3x squared minus 1. Okay? That's just from yesterday. That was f prime. So now let's find f double prime. Let's find the second derivative. Okay? Well, I'm just going to take the limit as h goes to 0 of f of x plus h squared, 3x plus h squared minus 1 minus f of x itself. Oh, relax, Carlos. And now let's evaluate. This one isn't that bad. There's no cube in it. So that would be a 3x squared plus 2xh plus h squared minus 1. And then bring in the negative minus 3x squared plus 1 all over h. Okay, so that would be a 3x squared plus 6xh plus 3h squared. Here we go, the fun part. So we've got a negative 3x squared and a positive 3x squared, a negative 1 and a positive 1, and that's it. So that gets me a 6xh plus 3h squared all over h. Cancel out an h. 6x plus 3h. And we're sending the limit as h goes to 0, which just basically gets us 6x. Just awesome over there. Just freshening up. We're just talking about second derivative. So I know f double prime of x is 6x. And again, we'll study the implications of how that relates to the graph, how that relates to velocities and stuff like that. You know what? Let's talk. Oh, good. The next. Ooh, I'm so excited. The next slide is talking about velocities. I was wondering if we were going to get to it in this lesson. In general, we can interpret a second derivative as the rate of change of a rate of change. Now, let me ask you: if I think about how fast does velocity change? How fast does velocity change? What am I actually asking about that? Acceleration. If I'm thinking about the change in velocity, I am accelerating. So that must mean that the derivative of velocity is acceleration, right? So we can also conclude the double derivative of position is acceleration, right? If we know the position function, s of t, if we take the derivative of s of t, we get velocity, right? And if I know the derivative of velocity is acceleration, then I can make this statement right here. Acceleration is equal to v prime, and acceleration is also equal to s double prime of t. We're not even going to look at the Leibniz notation down there because I like this prime notation much, much better. But that's a key concept that you have to learn. If you've got a position function, just find the double derivative, and there's your acceleration. If you've got a position function, find the derivative, that's your velocity. You know what the second semester is all about? How do we go backwards? How do we start at acceleration and end up at position? I know, that's how exciting.
So excited.
All right. Yeah, we didn't need to. It does talk about, the book talks about the triple derivative. Does anybody know what the change in acceleration would be? What that's called? Jerk. It's called jerk. Okay? So that means that you could keep this process going. You know, the triple derivative of s is jerk. Yeah, we won't really talk about that too much. But I just think that's kind of interesting that you could keep that process going. I wonder what the fourth derivative would be of position. What is the change in jerk? Oh, it's so stupid. So stupid. All right, so we found f double prime. Ooh, purple? No thanks. We found f double prime of x was 6x, right? Okay, what if I wanted to find f triple prime? What if I wanted to find the third derivative? Well, f of x would be, well, this would be f of x plus h minus f of x. Oh, sorry, yeah, f of x. Oh, no. F of x is just 6x. See, Carlos got me thrown off. Blame Carlos. All over h. So that would be 6x plus 6h minus 6x all over h. Now, what happens to my 6x's? They cancel. What happens to my h then? It cancels. So we're left with just 6. The limit as h goes to 0 of 6 is just 6. What's actually? What would the next one be? Well, so let's talk about the quadruple derivative, which has this notation. Now, if I go to plug in x plus h of just 6, well, it's easier once we get to this. If I go to plug in, let's see, it would be f of x plus h minus f of x all over h. I would say the limit as h goes to 0 is 0. And after that, it just keeps going to 0. Okay. So basically, what we're doing with the derivative is we just keep reducing it down and reducing it down and reducing it down until it gets to a point where it's 0, and then it will continue to be 0 forever and ever beyond that. So I know the homework looks like it's due on Monday. I would definitely spend some time over the weekend doing some of the homework, but I am going to give you Monday to work on this. Okay? Get a head start on it. It will take you more than just the period on Monday. So definitely get a head start on it so that you don't have too much to do Monday night. Deal? What a fun way to end the weekend. Or end the week.
End the weekend.
This is like the weekend. Just the weekends are like.
I want to